Look up on a clear night, away from the glow of cities, and you will see something every human who has ever lived has seen. Stars, thousands of them scattered across the darkness like distant campfires. For most of human history, this sight inspired wonder. It made us feel small, but it also made us feel centered. The stars were there. We were here. The universe seemed ordered, structured, almost understandable. It felt like there was a place for everything. That sense of order did not survive the 20th century. About 100 years ago, we discovered something that quietly dismantled our intuition about the universe. The cosmos is not static. It is not frozen in place. It is expanding. Every galaxy beyond our own is moving away from every other galaxy. And the farther away it is, the faster it recedes. This is not theory. It is not speculation. We can measure it directly in the light itself, stretched and reddened as space grows between distant galaxies. At first, this discovery seemed simple enough. The universe is getting bigger. But almost immediately, it raised a question that refused to go away. If the universe is expanding, what is it expanding into? The question feels obvious, natural, almost unavoidable. When a balloon inflates, it expands into the air around it. When a city grows, it spreads into the countryside beyond its borders. When anything we know expands, it moves into something that was already there. So surely the universe must be doing the same. Surely there must be something beyond it. But the universe is not a balloon. It is not a city. And the intuition behind the question may be wrong. This problem has haunted physicists and philosophers alike, not because it is complicated, but because it forces us to confront the limits of how our minds work. We evolved to think in terms of surfaces and edges, containers and boundaries. Inside and outside are among the most basic concepts we have. We understand what it means for something to be surrounded, but the universe does not care what our minds evolve to understand. Throughout history, we have repeatedly assumed that existence has edges. We believed the Earth was flat, with a boundary you could fall off if you traveled too far. When we learned the Earth was round, we imagined the solar system as a kind of cosmic island, with an edge where the sun's influence ended. Then we discovered the galaxy, vast and spinning, and we assumed that must be the boundary. Surely beyond our galaxy lay the final emptiness. Each time, we were wrong. The Earth has no edge because it curves back on itself. The solar system fades gradually into interstellar space with no sharp boundary. The galaxy is just one of hundreds of billions, scattered through a cosmos so large that language itself begins to strain. Every time we thought we had reached the edge disappeared. But this question feels different. Asking what lies beyond the universe is not like asking what lies beyond a continent or a star system. It is not about discovering a larger container. It is about asking whether the idea of a container applies at all. The expansion of the universe is real. We have measured it with extraordinary precision. We have traced it backward through time. We can reconstruct how galaxies move, how light stretches, how space itself grows. But understanding expansion is not the same as understanding what it means for space to grow. When astronomers say the universe is expanding, they do not mean that galaxies are flying outward into pre-existing emptiness. They mean that the distances between unbound objects are increasing because space itself is stretching. A familiar analogy is a balloon with dots drawn on its surface. As the balloon inflates, the dots move farther apart, but the dots are not moving across the surface. The surface itself is changing. In our universe, galaxies are like those dots. Space is the surface. And here is where intuition breaks. The balloon analogy works only if you imagine the surface, not the air around it. The air is not part of the analogy. There is no higher dimensional room the universe is expanding into. There is no external space waiting beyond the edge. As far as physics can tell, space is all there is. This expansion happens everywhere, all at once. There is no center, no edge, no special location. Every observer sees the same pattern: distant galaxies moving away, with speed increasing with distance. And then, in the late 20th century, the story became stranger. Astronomers studying distant supernovae expected to find that the expansion was slowing down. Gravity pulls matter together. Over time, it should gradually decelerate the outward motion that began with the Big Bang. Instead, they found the opposite. The expansion was accelerating. Something was pushing against gravity. Something was driving space itself to stretch faster and faster. We named this influence dark energy, not because it is understood, but because it is not. Dark energy appears to make up nearly 70% of everything in the universe. It does not thin out as space expands. As space grows, more dark energy comes into existence, filling the new space and pushing even harder against gravity. The universe is not just expanding, it is being pulled apart. This acceleration means the question is no longer academic. It is no longer just philosophical curiosity. It shapes the ultimate fate of everything that exists. Galaxies not bound together will drift beyond reach. Light emitted today will never arrive. Regions of the universe will disappear, not because they are destroyed, but because space grows too fast between us and them. And still, the question remains: if space itself is expanding, if there is no outside, no container, no edge, then what does into even mean? To answer that, we must first let go of the idea that the universe behaves like anything we know. And in doing so, we begin to glimpse just how strange reality truly is. The story of our cosmic horizon begins 13.8 billion years ago, at the very start of everything. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Every point in the universe, every location where matter and energy would eventually form galaxies, stars, and planets, existed in an infinitely dense, infinitely hot state. There was no center to this event. There was no edge. The Big Bang happened everywhere at once. This is difficult to picture. We're used to explosions that start at a point and expand outward into surrounding space. But the Big Bang had no surrounding space. Space itself came into being in that moment, already filled with energy, already expanding. Imagine the universe as the surface of a balloon. As the balloon inflates, every point on the surface moves away from every other point. No point is special, no point is the center. The expansion happens everywhere simultaneously. That's roughly what cosmic expansion is like, except it happens in 3 dimensions rather than on a 2-dimensional surface. In the first moments after the Big Bang, the universe was far too hot and dense for matter, as we know it, to exist. Particles and radiation existed in a churning, opaque plasma. Light couldn't travel freely. It scattered constantly off charged particles, trapped in an endless dance of absorption and emission. As the universe expanded, it cooled. After a few minutes, the first atomic nuclei formed. After several 100,000 years, the temperature dropped enough for electrons to bind with those nuclei, creating the first complete atoms. This moment changed everything. With charged particles now locked into neutral atoms, light suddenly had room to move. The universe became transparent. Photons that had been trapped since the beginning could finally travel freely through space. They've been traveling ever since. We can still detect these ancient photons today. They've been stretched by cosmic expansion, shifted from visible light into microwaves. We call this radiation the cosmic microwave background, and it marks the earliest moment we can observe. When we look at this faint glow in every direction, we're seeing the universe as it was roughly 380,000 years after the Big Bang. This ancient light forms a boundary to our observations. We cannot see beyond it, not because nothing existed before it, but because the universe was opaque to light before this moment. The cosmic microwave background is the farthest thing we can observe, the edge of our cosmic horizon in time. But here's where things become interesting. That boundary keeps moving. Light travels at a fixed speed, but the universe keeps getting older. Every second that passes, light from more distant regions has time to reach us. Our observable universe is constantly growing, like an expanding bubble centered on Earth. Think of it this way. Right now, there are galaxies whose light is just reaching Earth for the first time. Yesterday, they were beyond our horizon. Today, they cross into view. Tomorrow, even more distant objects will become observable. This boundary, the particle horizon, represents the maximum distance light could have traveled since the beginning of the universe. It expands at the speed of light, revealing approximately 1 light-year of new space every year. In cosmic terms, that's extraordinarily slow. But over billions of years, it adds up. The universe we can see today is much larger than the universe we could have seen 1 billion years ago. And 1 billion years from now, our descendants will be able to observe an even larger volume of space, assuming they have the instruments to detect such distant objects. This might suggest that given enough time, we'll eventually be able to see everything. If our observable universe keeps growing, won't it eventually encompass the entire cosmos? That would be true if the universe were expanding at a constant rate or slowing down. But the universe isn't doing either of those things. Space itself is stretching. Galaxies aren't moving through space so much as being carried along as space expands between them. The farther apart two galaxies are, the more space lies between them. And the more space between them, the faster they appear to recede from each other. This is Hubble's law, discovered nearly a century ago. The recession velocity of a galaxy is proportional to its distance. Nearby galaxies recede slowly. Distant galaxies recede quickly. Very distant galaxies recede very quickly indeed. At some distance, currently around 14 billion light-years, galaxies recede from us at the speed of light. Beyond that distance, they recede even faster. Space between us and them expands so rapidly that light itself makes no progress toward us. This doesn't violate Einstein's relativity. Nothing is moving through space faster than light, but space itself has no speed limit. It can expand as fast as it wants, carrying distant galaxies away from us at speeds that exceed light. And that's not the strangest part. For most of the universe's history, expansion was slowing down. Gravity pulled everything together, fighting against the initial expansion. We expected this. We predicted it. We built our models of cosmology around it. Then, about 2 decades ago, we discovered something unexpected. The expansion of the universe isn't slowing down anymore, it's speeding up. Something is pushing space apart. We call it dark energy, though we don't really know what it is. We just know it's there and it's winning. Whatever dark energy is, it makes up about 70% of the total energy in the universe, and its influence grows stronger as space expands. This changes everything about our cosmic horizon. It means our observable universe won't keep growing forever. It means there are regions of space we can see now that we won't be able to see in the future. It means the universe we inhabit is gradually shrinking in scope, even as it grows in size. Our horizon expands at the speed of light, revealing new regions of space with each passing moment. But the universe itself expands far faster. And that creates a peculiar problem. There's a distance in space where something remarkable happens. It's called the Hubble sphere, and it marks the boundary where the expansion of space exactly balances the speed of light. Inside this sphere, galaxies recede from us slower than light travels. Their light can make progress toward us, fighting against the expansion of space, gradually closing the distance. Given enough time, we'll see them. Outside this sphere, galaxies recede faster than light. Their light still travels toward us at light speed, but space expands so rapidly between us that the light never gets closer. It's like running on a treadmill that's moving faster than you can run. You're moving forward, but you're actually falling behind. The Hubble sphere sits roughly 14 billion light-years away. Beyond it, galaxies are unreachable by light. Their photons struggle against the current of expansion and lose ground with every passing moment. You might think this means we can't see anything beyond the Hubble sphere, but that's not quite right. We can see galaxies beyond this boundary. In fact, most of the galaxies we observe are beyond it. How is this possible if their light can't reach us? The answer lies in the history of expansion. The universe hasn't always expanded at the same rate. In the early universe, expansion was slower. Gravity was stronger relative to the size of space, pulling back against the expansion more effectively. Light that was emitted billions of years ago from a distant galaxy started its journey when that galaxy was closer to us. Back then, it might have been inside the Hubble sphere. The light made progress toward us. But as the universe expanded and dark energy became more dominant, that galaxy crossed outside the Hubble sphere. It's now receding faster than light. The light, however, was already on its way. It had already covered enough distance that it could eventually reach us, even though the galaxy that emitted it is now forever out of reach. So when we look at the most distant galaxies, we're seeing objects that are now beyond the Hubble sphere. We're seeing light from their past, from a time when they were close enough to communicate with us. But we'll never see what those galaxies look like today. Their present moment is hidden from us permanently. This creates a peculiar situation. Our observable universe contains galaxies we can see but can never visit. We can detect their ancient light, but we can never send a signal that will reach them. Even if we sent a message at light speed, it would never arrive. Space expands too quickly for the signal to make progress. These galaxies exist in a kind of cosmic exile. We can see their past but never interact with their present. And the situation gets worse over time. Remember that dark energy is causing expansion to accelerate. As billions of years pass, more and more galaxies will cross beyond the Hubble sphere. They'll join the ranks of the unreachable, visible only through the ancient light they emitted when the universe was younger. Eventually, there will be a final moment when light from these galaxies reaches us. After that, no more photons will arrive. The galaxies will fade from view, disappearing beyond an expanding boundary of darkness. This boundary is called the cosmic event horizon. It's different from the particle horizon we discussed earlier. The particle horizon represents the distance light has had time to travel since the Big Bang. It expands as the universe ages. The cosmic event horizon represents the distance beyond which events happening now will never be visible to us, no matter how long we wait. It doesn't expand. In fact, in terms of the galaxies it contains, it actually shrinks over time as galaxies cross from the reachable to the unreachable. Right now, the cosmic event horizon sits roughly 16 billion light-years away. Any galaxy beyond this distance is permanently beyond our reach. We'll never see it. We'll never communicate with it. We'll never know what happens there, and here's the truly sobering part. Most of the universe lies beyond this horizon. Our observable universe contains about 2 trillion galaxies. But the total universe, the space beyond what we can see, is almost certainly far larger. Some estimates suggest the universe beyond our cosmic horizon is at least hundreds of times larger than what we observe. Other models suggest it might be infinite. Either way, the vast majority of reality is already lost to us. We're cut off from it by the relentless expansion of space. Our own local galaxy cluster, the roughly 50 galaxies bound together by gravity in our cosmic neighborhood, will remain observable. Gravity holds us together more tightly than expansion can pull us apart. We'll always be able to see Andromeda, the Triangulum galaxy, and the other members of our local group. But nearly everything else will eventually disappear. Billions of years from now, astronomers living on Earth or whatever worlds survive the aging of our sun will look out at a much emptier universe. The distant galaxies that fill our telescopes today will have faded beyond the cosmic event horizon. The cosmic microwave background will have been stretched to such long wavelengths that it becomes undetectable. Future observers will see only the galaxies in our local cluster, surrounded by darkness. They'll have no way of knowing that billions of other galaxies once filled the observable universe. They'll have no evidence of the Big Bang. They'll have no way of discovering that space expands. They'll live in a profoundly smaller, observable universe than we do, isolated in an island of light, surrounded by an ocean of darkness. We live in a privileged moment in cosmic history. We exist at a time when the universe is old enough for galaxies to have formed and young enough for distant galaxies to still be visible. We can observe the evidence of cosmic expansion before it carries that evidence beyond our reach. This is our window of opportunity. This is when we can study the cosmos in its full scope, before most of it disappears forever beyond our cosmic horizon. If we can never observe these distant regions, can we still know what exists there? Mathematics and physics offer unexpected insights. We can't see beyond our cosmic horizon. We can't send probes there. We can't receive signals from those distant regions. And yet, we're not completely in the dark about what lies beyond. Science gives us tools to infer properties of things we cannot directly observe. We use these tools every day without thinking about them. You can't see individual atoms, but you know they exist. You can't see the core of the Earth, but you know it's made of iron and nickel. You deduce what you cannot observe from what you can measure. The same principle applies to the universe beyond our horizon. The foundation of our understanding rests on something called the cosmological principle. It's a simple idea with profound implications. The principle states that on large enough scales, the universe looks roughly the same everywhere. No location is special. No direction is privileged. The cosmos is homogeneous and isotropic. This isn't just a philosophical assumption. We have evidence supporting it. Look at the cosmic microwave background, that ancient light from the early universe. It's remarkably uniform. The temperature varies by only about 1 part in 100,000 across the entire sky. The universe, at least as it was 380,000 years after the Big Bang, was extraordinarily smooth. Today's universe shows more structure. Galaxies cluster into groups. Groups collect into superclusters. Superclusters arrange themselves along vast filaments of matter, separated by enormous voids containing almost nothing. This cosmic web stretches across space in every direction we can observe. But here's what's important. When we zoom out far enough, when we look at volumes of space hundreds of millions of light years across, the distribution becomes uniform again. The number of galaxies in one huge volume of space roughly matches the number in another equally huge volume elsewhere. East looks like west. North looks like south. The distant universe in one direction appears statistically identical to the distant universe in any other direction. This uniformity suggests something profound. If the universe looks the same in all directions from our viewpoint, and if no location is special, then the universe should look roughly the same from any viewpoint. An observer in a galaxy 10 billion light-years away should see the same general patterns we see, the same types of galaxies, the same large-scale structure, the same physical laws governing the behavior of matter and energy. We can test this idea, at least partially. We can observe galaxies at different distances, which means observing them at different times in cosmic history. We can see how structure evolved. We can check whether the laws of physics appear to change with location or time. So far, everything checks out. The speed of light appears constant everywhere we look. The strength of gravity seems the same in distant galaxies as it is here. The behavior of atoms billions of light-years away matches the behavior of atoms in laboratories on Earth. Physical constants appear truly constant. Physical laws appear truly universal. This gives us confidence that the universe beyond our horizon resembles the universe we can see. The same kinds of galaxies probably exist there. Stars form and die in roughly the same ways. Planets orbit those stars. The chemistry of distant, unobservable regions likely mirrors the chemistry we observe. But resemblance goes deeper than that. The cosmic microwave background doesn't just tell us about uniformity, it also tells us about the geometry of space itself. By measuring tiny variations in the temperature of this ancient light, cosmologists can determine whether space is flat, curved like a sphere, or curved like a saddle. The answer appears to be that space is flat, or at least very close to flat. This measurement has been refined over decades, and the result keeps pointing to the same conclusion. Within the limits of our instruments, the universe has zero curvature. A flat universe can extend infinitely in all directions. It doesn't have to curve back on itself. It doesn't have to close into a finite volume. Flatness is consistent with, though it doesn't prove, an infinite cosmos. If the universe is truly infinite, then the unobservable region beyond our horizon is also infinite. And it contains infinitely more galaxies, infinitely more stars, infinitely more planets than we can ever hope to see. But even setting aside the possibility of infinity, we can make statistical arguments about the unobservable universe. Our observable universe is large. It contains trillions of galaxies spread across billions of light-years. That's a substantial sample size. And in that sample, we see no evidence that we occupy a special location. We're not at the center of anything meaningful. We're not in a region with unusual density. We're not surrounded by atypical structures. Everything we observe suggests we're in an ordinary part of space, with ordinary galaxies and ordinary physical conditions. If our location is typical, then the regions beyond our horizon are likely typical as well. They probably contain the same kinds of structures, the same distribution of matter, the same balance of ordinary matter, and dark energy. There's a theory called cosmic inflation that strengthens this argument. According to inflation, the entire observable universe, and far more, emerged from a tiny patch of space that underwent exponential expansion in the first fraction of a second after the Big Bang. This inflationary period stretched quantum fluctuations to cosmic scales, creating the seeds that eventually grew into galaxies and clusters. But it also means the observable universe came from a region so small that it was effectively uniform. Any variations were smoothed out by the dramatic expansion. If inflation is correct, and most cosmologists think it is, then the universe beyond our horizon came from the same tiny, uniform patch. It underwent the same expansion. It experienced the same physical processes. It should look fundamentally similar to what we observe. All of this points toward a conclusion that's both comforting and humbling. The unobservable universe probably isn't radically different from what we can see. It's not populated by strange, exotic structures that violate everything we know. It's likely just more of the same. Galaxies and stars and planets extending beyond the limits of our vision, following the same laws, built from the same matter, shaped by the same forces. We can't prove this. We can't confirm it through direct observation. But the evidence we do have suggests the universe is uniform on the largest scales, and that uniformity likely extends beyond what we can see. But resemblance isn't certainty. When we venture beyond direct observation, we enter the realm where physics becomes philosophy. The universe beyond our horizon likely resembles what we can see, but likely isn't the same as certain. And when we ask what lies beyond the edge of everything, we're forced to consider possibilities that stretch beyond comfortable assumptions. Start with something fundamental, the shape of space itself. We've measured the curvature of the universe and found it appears flat. But measurements have limits. They have error bars. Space could have a very slight curvature that our instruments can't detect. And if space curves even slightly, the implications change dramatically. A spherical universe curves back on itself like the surface of a ball. Travel far enough in one direction, and you'd eventually return to your starting point. Such a universe would be finite, vast, beyond imagination, but bounded. There would be a specific, countable number of galaxies, a fixed amount of matter, a total volume of space. A hyperbolic universe curves in the opposite way, like a saddle. It would be infinite, but with a different geometry than flat space. Parallel lines would diverge. Triangles would have angles that sum to less than 180 degrees. The rules of geometry we take for granted would subtly differ. Our measurements suggest flatness, but they can't rule out slight curvature one way or the other. The universe could be a three-dimensional sphere so large that within our observable region, the curvature is too small to detect. Like standing on Earth's surface, it looks flat locally, but curve it does. Then there's topology, the way space connects to itself. Even a flat universe might not be simply infinite. Space could wrap around in strange ways. Imagine a universe where traveling far enough in one direction brings you back from the opposite direction, like a video game where leaving the screen on the right makes you reappear on the left. A flat torus is one such topology. Space could be finite but have no edge, looping back on itself in all three dimensions. You could theoretically see multiple images of the same galaxy in different directions, viewing it from different angles as light takes different paths through wrapped space. We've looked for evidence of such topology. We've searched for repeating patterns in the cosmic microwave background that might indicate wrapped space. So far, we've found nothing. If the universe does loop back on itself, it must do so on scales larger than we can currently observe. But the absence of evidence isn't evidence of absence. The topology of space remains an open question. Now consider what happens if space is truly flat and infinite, extending forever in all directions. An infinite universe contains infinite matter, infinite galaxies, infinite stars, infinite planets. And here's where things become philosophically troubling. In an infinite universe with matter distributed uniformly, every possible arrangement of particles would occur infinitely many times. The laws of probability guarantee it. Given infinite space and infinite matter, anything that can happen will happen. Not just once, but infinitely often. Somewhere beyond your cosmic horizon, there would be another galaxy that looks exactly like the Milky Way. Another solar system identical to ours. Another Earth with the same continents, the same cities, the same history. Another you reading these words at this exact moment. In fact, there would be infinitely many such copies. Some identical down to the quantum level, others differing in small details, others diverging in dramatic ways. Every possible variation on your life, every choice you didn't make, every path you didn't take, all of them realized somewhere in the infinite expanse. This isn't science fiction. It's a mathematical consequence of infinity combined with finite possibilities. There are only so many ways particles can arrange themselves in a given volume of space. Make the space infinite, and every arrangement must repeat. Most physicists find this implication uncomfortable, but discomfort doesn't make it false. The situation becomes even stranger when we consider cosmic inflation more carefully. Inflation explains why our universe is so flat and uniform. A tiny region of space expanded exponentially, smoothing out irregularities and creating the vast cosmos we observe. But in most models of inflation, the process doesn't stop everywhere at once. Inflation ends in some regions, allowing normal expansion to take over. Those regions become pocket universes like ours, filled with galaxies and stars. But between these pockets, inflation continues, exponentially expanding and spawning new pockets in an eternal, self-reproducing process. This is called eternal inflation, and if it's correct, our observable universe is just one bubble in an infinite foam of universes. Each bubble might have different properties, different physical constants, different laws of physics. In some bubbles, electromagnetism might be stronger. In others, gravity might be weaker. Some bubbles might have more dimensions of space. Others might have different particle physics, making atoms impossible and life unthinkable. This vast collection of possibilities is sometimes called the multiverse. It's a controversial idea. Many physicists embrace it as a natural consequence of inflation. Others reject it as untestable speculation that goes beyond what science can address. The landscape of possible universes might be truly vast. String theory, if it's correct, suggests something like 10 to the power of 500 possible vacuum states, each corresponding to a universe with different physical laws. That's more possible universes than there are atoms in our observable universe, by a margin so large it defies comprehension. In such a landscape, nearly anything becomes possible somewhere. Universes with dozens of dimensions, universes where particles behave in ways we'd consider magical. Universes hostile to any form of structure, collapsing back on themselves or expanding too rapidly for matter to clump. Our universe, with its particular set of physical constants that allow stars and planets and life, might be just one outcome among countless others. We exist in this universe not because it's the only one, but because it's the kind that can produce observers to wonder about such things. These ideas push the boundaries of what we usually call science. We can't observe other universes, we can't test whether they exist, we can't measure their properties or confirm their physical laws. Does that make these questions meaningless? Or are there truths about reality that lie forever beyond the reach of observation? These theoretical frameworks stretch beyond current physics into questions that challenge the very meaning of existence. There's a line we eventually cross when thinking about the universe. On one side, we ask questions we might someday answer. On the other, we ask questions that may have no answer at all. What lies beyond our cosmic horizon falls somewhere near that line, perhaps on both sides of it. Science has always worked by making observations and testing predictions. You propose a hypothesis, design an experiment, collect data, and see whether reality agrees with your expectations. This process has given us nearly everything we know about the natural world. But what happens when the thing you want to study cannot, even in principle, be observed. The universe beyond our cosmic event horizon will never affect us. No light from those regions will ever reach Earth. No signal, no particle, no influence of any kind can cross that boundary. Causally, those regions are completely disconnected from us. Does it even make sense to ask what's there if we can never know? This is where science bumps against philosophy. It's where physicists disagree not just about answers, but about whether the questions themselves are meaningful. Some argue that science is fundamentally about what we can observe. If something cannot be observed, even in principle, it lies outside the domain of scientific inquiry. Asking about the unobservable universe is like asking what happened before the Big Bang, a category error that misunderstands what questions science can address. Others argue that reality doesn't care about our observational limits. The universe beyond our horizon either exists or it doesn't. Either it contains galaxies or it doesn't. Either space extends infinitely or it doesn't. These are matters of fact, even if we can never confirm them. The debate touches on something deeper. What makes a scientific theory valid? Karl Popper, a philosopher of science, argued that theories must be falsifiable to count as scientific. A theory that makes no testable predictions that cannot be proven wrong isn't really science. It's speculation dressed in scientific language. By this standard, claims about the unobservable universe might not be scientific. We can't test them. We can't falsify them. We're left with mathematics and logic, which can tell us what's consistent with our observations but can't tell us what's actually true beyond them. But science has always dealt with the unobservable in a sense. You can't observe an electron directly. You observe its effects, tracks in a cloud chamber, patterns on a detector, the behavior of materials. You infer the electron's existence and properties from these indirect observations. You can't observe the core of the sun. You deduce its temperature and density from models of stellar physics, confirmed by observations of the sun's surface and the particles that escape from its interior. Much of science involves inferring what we cannot see from what we can measure. The universe beyond our horizon might be an extreme case, but it's not fundamentally different in kind. And there may be ways to constrain possibilities, even if we can't observe distant regions directly. The cosmic microwave background carries information about the early universe. Future measurements might reveal subtle patterns that hint at larger structure beyond our horizon. If the universe has a finite topology that wraps around, we might detect repeating patterns in the distribution of galaxies or the temperature of ancient light. Gravitational waves offer another window. These ripples in space-time travel at light speed, but they interact very weakly with matter. A gravitational wave generated in the early universe might carry information about conditions beyond our current cosmic horizon, information encoded in its frequency and amplitude. Cosmic inflation itself makes predictions we can test. Different models of inflation predict different patterns in the cosmic microwave background, different levels of gravitational waves, different distributions of matter. If we can confirm or rule out specific inflationary models, we learn something about what happened beyond our observable region. These observations won't show us what's beyond our horizon today, but they might tell us whether our assumptions about uniformity and universality are correct. They might reveal whether the unobservable universe follows the same rules as the observable one. Still, there's a hard limit to what we can ever know. Some questions may genuinely be unanswerable. If the universe is infinite, we can never confirm that infinity through observation. We can only say that it's larger than we can see and consistent with being infinite. If other universes exist beyond our own, separated by eternally inflating space, we can never visit them or communicate with them or even detect them directly. Their existence might be suggested by theory, but never proven by observation. If physical constants are different in distant regions beyond our reach, we have no way to measure those differences. We can only speculate based on theoretical models that might or might not reflect reality. This is uncomfortable for science. We're used to seeking answers. We build better telescopes, design more sensitive detectors, develop more sophisticated theories, and gradually expand what we know. The idea that some questions might be forever beyond reach challenges the optimism that drives scientific inquiry. But perhaps there's a different way to think about it. Asking what lies beyond our cosmic horizon doesn't require that we find a definitive answer. The value might be in the asking itself, in pushing our understanding as far as it can go, in mapping the boundaries of knowledge, in recognizing both what we can know and what we cannot. Science has always been about exploring the limits of the observable world. Sometimes those limits turn out to be farther away than we thought. Sometimes they're closer. But identifying where they lie is itself a form of knowledge. We may never know what lies beyond our cosmic horizon with certainty, but we can know what's consistent with our observations. We can know what's likely given the patterns we see. We can know what questions are answerable and what questions will always remain beyond our grasp. That's not nothing. That's the map of reality as far as we can draw it, and the honest acknowledgement of where the map must end. Yet even at the edge of knowledge, we find something unexpected, a profound connection between the largest and smallest scales. We've spent all this time asking what lies beyond the edge of the universe. But perhaps the more remarkable thing is that we can ask the question at all. Think about what had to happen for this moment to exist. The universe had to begin in a particular state, smooth enough to allow structure to form, but not so smooth that nothing interesting ever happened. Physical constants had to fall within narrow ranges that permit atoms and chemistry and complexity. Stars had to form and die, forging heavy elements in their cores and scattering them across space. Planets had to coalesce from that enriched material. On at least one planet, chemistry had to organize itself into something we call life. That life had to evolve over billions of years into organisms capable of asking questions about their cosmic origins. And then those organisms had to develop tools, mathematics, telescopes, theories of physics, sophisticated enough to probe the nature of reality itself. All of this had to happen within a universe structured in such a way that the past remains visible, that evidence persists, that the cosmos can be understood. We exist at a cosmic intersection. We're made of atoms forged in stars. We live on a planet formed from the remnants of earlier stellar generations. We look out at a universe old enough for us to have evolved, but young enough that we can still see its distant reaches. This is not an accident, or rather, it's the only kind of accident that could produce observers wondering about it. There's something profound in realizing that the universe has fundamental limits, and that we do too. Just as there's a cosmic horizon beyond which we cannot see, there's a quantum horizon below which we cannot measure. The Heisenberg uncertainty principle ensures that some aspects of reality remain fundamentally fuzzy, resistant to perfect knowledge. In both directions, toward the infinitely large and the infinitely small, we encounter boundaries to what we can know. The universe doesn't owe us complete transparency. Reality has layers we cannot access, questions we cannot answer, truths we cannot verify. And yet, within those limits, we can understand an extraordinary amount. We know how stars work. We know how galaxies form. We know the age of the universe to within a tiny margin of error. We've mapped the cosmic microwave background and traced the evolution of structure across billions of years. We've discovered planets around distant stars and detected gravitational waves from colliding black holes. All of this knowledge emerged from creatures living on a small planet, orbiting an ordinary star in an unremarkable galaxy. Creatures who have only existed in anything like their current form for a few 100,000 years. Creatures who've only had telescopes for a few centuries. The fact that we can know anything about the universe beyond our immediate surroundings is remarkable. The fact that we've mapped the observable cosmos, understood its history, and identified the limits of our knowledge, that's astonishing. Our observable universe, constrained though it is, contains wonders enough for many lifetimes of exploration. 2 trillion galaxies, hundreds of billions of stars in each, uncountable planets, nebulae where stars are born, supernova remnants where they die, black holes, neutron stars, quasars, and structures we're only beginning to understand. We don't need access to the entire universe to find meaning or purpose in studying it. What we can see is more than sufficient to occupy our curiosity for as long as our species endures. And there's a bittersweet element to our cosmic moment. Future generations will not have the view we have. As expansion accelerates, galaxies beyond our local cluster will fade from sight. The cosmic microwave background will stretch to undetectable wavelengths. Evidence of the Big Bang will disappear. Astronomers billions of years from now will look out at a universe that seems static, small, and isolated. They'll have no way of knowing about the vibrant cosmos that once filled their telescopes. They'll lack the evidence we possess. They'll be cosmically poorer for it. We live in a window of visibility. We exist at a time when the universe is old enough to have produced complex structures, but young enough that those structures remain observable. We can see both the distant past through ancient light and the broad expanse of space through modern instruments. This privilege comes with a responsibility. If we're the observers fortunate enough to witness the universe in its full observable scope, we should observe it well. We should map it, study it, understand it as thoroughly as we can. We should preserve that knowledge for whoever comes after, even if they can no longer confirm it through direct observation. But perhaps the deepest insight is this. Asking what lies beyond the edge pushes us to confront what it means to exist in the first place. We are temporary patterns of matter and energy, briefly organized into forms capable of self-reflection. We exist in a universe that's mostly empty space, governed by laws we didn't choose, within horizons we cannot cross. And yet, within those constraints, we find meaning. We create art and music. We love and grieve. We wonder and explore. We ask questions about things we'll never see, reach for understanding we'll never fully grasp, and find that the reaching itself gives our existence shape. The universe beyond our horizon doesn't need to be known to be real. Its existence doesn't depend on our observation. Reality unfolds whether we witness it or not. But the fact that we're here, that we can think about these questions, that we can map the boundaries of the knowable and acknowledge the vast unknown beyond, that says something about what the universe is capable of producing. Matter can organize itself into consciousness. Atoms can contemplate their origins. The universe can develop the capacity to wonder about itself. In asking what lies beyond the edge of everything, we're really asking what we are. We're exploring the limits not just of the cosmos, but of understanding itself. We're discovering what it means to be a finite being in an infinite reality, a brief pattern of awareness in an ancient and indifferent universe. The answer to what lies beyond our cosmic horizon may be simple. More space, more galaxies, more of what we already see, extending beyond the reach of observation. Or the answer may be strange beyond imagining. Other universes with different laws, infinite variations on reality, structures and possibilities we lack the concepts to describe. We may never know for certain. And that's all right. The universe has given us the ability to ask. The universe has given us the tools to explore as far as observation allows. The universe has given us this moment, this view, this chance to contemplate our place in the cosmic vastness. That's enough.